We are going to continue on here. We got a little bit into chapter one last time, and like I mentioned before, you are responsible for chapter one. Uh, a lot of chapter one, though, is, as I mentioned before, there's a lot of kind of math review in that chapter, could be very helpful if you need it. They do talk a little bit about rearranging formulas. They also talk a number of places, I think, in chapter one about using your calculator and sort of the buttons and stuff like that. So you definitely, maybe for sure, are responsible for that material. You should read through it. Again, if you need some help on some of that, you might be able to find, some answers in there. They talk about basic math operations, adding negative numbers, multiplying negative numbers, all that kind of stuff, rearranging things. So definitely can be very helpful. In addition to obviously knowing that from chapter one, we did talk about the scientific method, which you do need to know a little bit about. But really, the main part of chapter one that you will be responsible for is sort of where we're going to kind of finish up on. So again, although in class here we may not cover every single section in chapter one, because a lot of it is that kind of review information, make sure you just kind of don't blow over. You take a look at it and you understand what's going on there. All right, so last time we really talked about a couple of things that you'll actually see in a little later chapter, but we talked about matter. And we talked about the three states of matter, which is, again, our solid, our liquid, and our gas state of matter. And as we talked about in the solid state of matter, once again, things are usually packed in really tight to one another. There's usually not a lot of room for movement. It is not a lot of energy happening at that point, which is why they're really kind of stuck together like so. In the liquid state, once again, still relatively close to one another, but they do have a little bit more energy. And because of that, they're able to kind of move past each other. And again, that's why we even think about liquids. They're thought of obviously as being fluid. In the gas state, everybody again has a lot of energy because they basically have broken apart from one another. They're flying around, they're causing collision, which is what we associate pressure with, that we associate with gases. We talked a little bit about the transitions here. Again, as you go from solid to liquid, that is the process of melting. Going from liquid back to solid is the process of freezing. Liquid to gas is the process of evaporation or vaporization. Gas back to liquid is our condensation. As we also talked about, solid, skipping the whole liquid cleanup there, going to be our sublimation. And gas back to solid, also skipping the liquid deposition. And these are sometimes referred to as changes of state. And we really talked about a little bit in this chapter in context of sort of, what is chemistry. And chemistry really is a study of matter. And matter, again, could have anything that occupies space and has mass. And one of the major things, or a lot of things that we look at are as matter sort of changes from one state to the next, what's happening. We also talked about the energy sort of component to this. And in terms of energy, energy needs to be put in or absorbed when we are going from solid to liquid to gas. Again, the example like we talked about, which is our ice cube example, again, is going to pick up energy and start to melt. Liquid water, you put energy in, like putting a fire underneath it to boil water. Will then start to boil and become gas. Those are all processes where energy is absorbed, and that is what's known as endothermic processes. So endothermic basically means any process where heat or energy is being absorbed. And the opposite is true as we go from gas to liquid to solid. These are all processes where energy is released, and that is exothermic, is that process where energy is released. And one of the major things that we look at in terms of chemistry is really energy flow as well. what's happening with energy. Is somebody gaining energy? Is somebody releasing energy? Is this chemical reaction overall exothermic and releasing energy? Is this reaction endothermic and gaining energy? So these are very big sort of components of chemistry and what we study. We will get more into detail on some of this in chapter 3 in terms of energy and different states of matter. But again, just a little preview there. Any questions on that stuff we talked about last time? Okay. So we're going to pick up with really the two last things I really want to kind of for sure go over in this chapter, and that is really scientific notation. And I'd say in most books it's usually in chapter 2, but we'll talk about it officially here. I would say out of chapter 1, this is probably the big topic, yeah, that you really need to focus on. Um, Scientific notation is a way that we write numbers when we have really large numbers or we have really small numbers. And when you have really large numbers or you have really small numbers, obviously you're going to have probably a lot of zeros. And if you write numbers sort of in decimal form, or sometimes referred to as positional notation, you're probably going to lose some digits or lose some zeros along the way if you're doing a lot of calculations. So clearly, if you had a number like, 126,000, you definitely would perhaps lose a few zeros along the way if you're doing some calculations with that number or copy it wrong and stuff like that. So to handle these sort of really large numbers or these really small numbers, we oftentimes will write numbers in scientific notation. And scientific notation has a general format of n times 10 to the n. And this first n is a number between 1 and 10. Now, it usually is not 10. It can actually be 1, it's okay. But not 10, so it's got to be less than 10 and basically 1 and above. And the times 10 part here to the little n, this little n can either be a positive or negative number. And really what determines whether or not it's positive or negative is basically which way you got to move the decimal point to get it to a number between 1 and 10. And that is the general format. As you can see here, we have 1 times 10 to the 5. So here's our 1, which would be the end part. This 5 is the little end. This is 8 times 10 to the minus 6. That's the big end part. Negative 6 here is our little end part there on the other part of the number. So if I had something like 0.4326 and I wanted to write it in scientific notation, the first thing we're going to do is move that decimal point whichever way is going to get us a number between 1 and 10. Now, clearly, if I move it to, I'm going to get me close to 1 and smaller. So in this particular case, I do need to move the decimal point to the right. And if I move it just one place to the right, I end up with 4.326 times 10 to the negative 1. This is a number between 1 and 10. I moved the decimal point one place to get it between 1 and 10. It is negative because I moved the decimal place to the right. A good way to remember it is typically things with negative exponents are small numbers, less than 1. Yeah, so if it's like a small number, it should have a negative exponent. Now that's different than if I had 123.5 and I want to write it in scientific notation. Once again here, we would need to move the decimal place to the left in this case. It goes from 123 to 12.3. 12.3 is greater than 10, so we need to keep going. We need to go one more place. And now I have something like 1.235, which definitely is between 1 and 10. And this would give me 1.235 times 10, and I moved it 2 places. And it is going to be a positive exponent in this case because we moved the decimal place to the left. Or you can remember if it's greater than 1 or a large number, you should end up with a positive exponent when you do that. First off, any questions on that there? Now, if you have a number that does not have, obviously, a decimal point in it, we do our normal assumption, which is we assume the decimal point is where? If there's not one written. We do assume, yeah, it's at the very end. Yeah. So if there is not one written, we then assume in the case of scientific notation, we don't assume it in other situations that there's a decimal point there, but we assume it's there. And then we would need to go 1, 2, and 3 places here to the left, giving us 3.254 times 10 to the 3. Again, large number, positive exponent, move the decimal point to the left. Any questions on how to do that there? Now, here again, if we look at this, 0.000008, we're going to go one place, not going to give us a number between 1 and 10, 2, 3, 4, and 5, and one more makes 6. And that moves us to 8 times 10 to the minus 6 meters in this particular case. Once again here, we would assume our decimal points at the end. 1, 2, 3, 4, and 5 places to the left, giving us 1 times 10 to the 5. Now, you may be wondering why maybe I got rid of some zeros in this case. Maybe you're wondering why I kept all the numbers in these cases here. And there is a reason why we did that, and we do that, and it's really in chapter 2, which we'll talk about, but we'll just kind of talk about it a little bit here, and then when we get to chapter 2, we'll continue to talk about it. And it has to do with the idea of significant figures. And when you have a number and you're just, for example, turning it into scientific notation, or really in a lot of cases, if you can, going from scientific notation back to like decimal form, you should really keep all the significant figures the same. So you shouldn't lose any significant figures along the way. Now, one of the things when you look at a number that's actually written in scientific notation, when you have a number that's written in scientific notation like this, n times 10 to the n, all of the numbers that come before the times 10 part, these are always significant figures. So, for example, spell it all out there, figures. When we see this number written as 8 times 10 to the minus 6, there is only one number before the times 10 part, before this part of the number. And that would mean that this number written like this has one significant figure. And as we will learn later on, when we look at a number written like this, the only significant figure here is actually the 8, which is why we only keep the 8. We don't add extra zeros or anything like that. When we look at this number written in scientific notation, the 1 that comes before the times 10 part is one number, and this would have one significant figure. When we look at a number written in decimal form, or this kind of non-scientific notation form, that 1 is actually the only significant figure there is in that number, and that's why we, in this case, drop all the other zeros and we don't keep it. So the question about scientific notation is this: do you always have to give your answers in scientific notation? And the truthful answer is no, you do not, unless obviously it asks you to give your answer in scientific notation. But as we will learn and talk more about in chapter 2, when we really officially talk about significant figures, there is sometimes the only way that you could give your answer to the correct number of significant figures, which is something that you always want to do when you're doing calculations or whatever it may be, is to write it in scientific notation. There can be sometimes no way to write it like in decimal form and have the right amount of significant figures. So for example, if I had this number here, which is And we'll do 12,000, right? And let's just say, for example, we did a calculation, and this is what we got like staring at us on our calculator. Hopefully that's the right answer. And we know based on the calculation we did, we need three significant figures in our answer. Let's just say hypothetically, we need three significant figures. There is no possible way to write that number in that form and still have three significant figures. By the way, in this case, these are the only significant figures there are in that number, which is the 1 and the 2. So no matter how you do it, there is only two significant figures is the only way you could write that number and still have it mean 12,000. Could you do 120 and put a decimal at the end? You could, and it would be three significant figures, but there's a big difference between 120 and 12,000, so you'd actually change the meaning of the number. So there is no way in decimal form to get that significant figures. That is where scientific notation is very much helpful, because I could turn this into scientific notation again by going one place, two places, three places, four places to the left. And that would give me 1.2 times 10 to the 4. Now, the way I just wrote it, how many significant figures would it have? It would only have two, which without that big talk up there, I kind of screwed that up a little bit. Not a problem though, because I'm writing in scientific notation. I could quickly and very easily, by putting a 0 there, now this number has how many significant figures? It has 3, which is what I'm looking for in my made-up example here. So there will come times where, like, no matter what you do, there's just no way to get your answer to the right number of significant figures without doing it in scientific notation. And you can really control the number of significant figures when you write a number in scientific notation. Let's just say, for example, I didn't need 3 sig figs, but maybe I just needed 1. I could just very easily, just instead of that, go 1 times 10 to the 4. Now I got 1 significant figure, right? Maybe I needed 4 significant figures. I could add in a couple of extra zeros, and I know that everything before that times 10 part is significant. Now I got 4 numbers before it. Now I got 4 significant figures. So the sort of benefit of scientific notation is you have a lot of control over how many significant figures you can put in an answer. And like I said, not a lot of times, but every so often you'll come across an answer where there's just no way to do it and get the right number of significant figures without putting in scientific notation. Any questions on that there? Now, in addition to obviously writing something in scientific notation, if you had a number, obviously in scientific notation, like 3.2 times 10, and we'll do 3 maybe. And we wanted to put it, yes. I'm sorry. Say again. In terms of what yeah. Yeah, so it would depend in this particular example what comes after my original number of zeros. So you would be right. So for example, let's just say the number was 1, 2, 3, 4, 5. Very creative, I know, numbering. But let's just say this was the number that we got, and we wanted, like, you know, 3 significant figures still. At this point, if we were going to put it into 3 significant figures, we would go 1, 2, 3, 4, and here we would include the proper number that's there. Yeah. So if it's not zeros, like my original example, you would put the next number. You would also have to look, do you need to round that number or not, you know, where you're cutting it off. So you would look at that. But if it happens to be a number like the original number, 12,000, they're all zeros, then you could just add the zeros to get you what you need. Yeah. Other questions? All right, so let's say we have this number here and we want to turn it into just really like decimal form or a regular number. We would start with our 3.2. This 3 means that we are going to move the decimal place 3 places. And in this particular case, we see the exponent is a positive number, which should tell us this number is a large number, right? Not a small number. So that helps you decide which way you should go. If you're not sure, just go one way and see how you do. If I decided to go to the left, if I'm not sure, I end up with 0.32. That definitely is not making that number larger, right? So that definitely would not be the way to go. I would need to go this way, right? And if I go this way, for example, that now makes it 32, which is getting bigger, and that should be a larger number. So we go 1 place, 2 places, and 3 places. And we do need to add zeros. In this case, you would add zeros because you have no other numbers, obviously. So you would add zeros in this case. And we would end up with something like 3,200 here as our number. Yeah. If you had this number and you want to put it into scientific notation, no, it would still be the same as this. So again, if you were starting with this number, you would assume the decimal points here, and you would go 1, 2, 3 places, and that'll give you 3.2 times 10 to the 3. 3,200 is bigger than 1, so it's a large number, so it would be positive. The only way you would get a negative is you got to start with like a small number, like if you had something like this. Yeah, something like this, which is less than 1, which is a small number. You move the decimal point to the right, 1, 2, and 3 places. That'll give you 3.2 times 10 to the minus 3. I counted 1, 2, 3. In that case, yeah. Yeah. So this number here and this number here are the same number. They're just one's written in scientific notation, and one obviously is written in decimal form, if you want to call it that. Now, if you did have the negative exponent, once again, we would take the 1.25, and this negative 2 tells us it should be a smaller number, less than 1. And hopefully at this point, if you kind of go to the left here, that's going to turn it now into kind of a smaller number because you would put a 0. So now you're like at 0.01, which is now making it smaller. You go one more, pop a 0 in there. I think I got the right amount of zeros, maybe. 1, 2, 3. Right. Oh, I went too far, I think. I overshot my zeros there. Overshot my zeros. Take that off there. There we go. I think I still had the 3 in my head. All right. So we would go 1 and then 2. So 0.0. 1, 2. There we go. So we would end up with 0.0125. This also brings up a really good practice, which is if you have a decimal number that you're going to write, it is really good practice, and you should do it. You should have the 0 before the decimal point. That case, when you're doing calculations, if you don't have that extra 0 there, frankly, numbers tend to run together, and you're not really sure where one ends and another one begins. So it's really good practice. If this was like your answer, that you do put that 0 in front of the decimal and not just give the answer like this with nothing there. Try to avoid doing that again so numbers don't run together. Now, we're talking a little about significant figures, and it's also a very common error that people make, which is they have a number like we have here written in scientific notation, or even the one down there, 1.25 times 10 to the minus 2. And maybe they're asked just a simple question of, like, how many significant figures does it have, right? How many significant figures does this number have? It is 2 significant figures, right? How many significant figures does this number have? It is 3 significant figures. But what people always kind of want to do when they're asked a question like that is they want to unconvert it out of scientific notation and put some zeros on it. And people end up getting the wrong number of significant figures because now they're like, oh, should I count those zeros? Should I not count those zeros? And it's a very common mistake that people make. So just remember, if you need to kind of figure out, or you're asked a question, or again in a calculation, figure out how many significant figures a number has, and that number is written in scientific notation. Just look at the number when it's written in scientific notation, and however many numbers are there is the right amount of significant figures it should have. So a very common thing is like people always want to kind of put it into a regular number, and then you have to add some zeros, and people oftentimes will give the wrong answer. So for example, hypothetically speaking, people will write that on their paper and go, it has four significant figures, even though in reality those zeros are not significant. And that's a very, very super common error that people make. We'll talk why those are not in chapter 2, but trust me, they are not. And that's why if you do have it in scientific notation, if you need to know how many significant figures, just look at the number as it's written in scientific notation, and it'll give you the number of significant figures. Any questions? Yeah. No. Well, yeah, yeah. Any non-zero would be a significant figure. But within a number that's greater than zero, you can have some numbers that are not significant. For example, like my 3200, clearly that's bigger than zero. But in that particular number, the way it's written, only the three and only the two are significant. Those zeros at the end are not significant. So any non-zero number that you see for sure is going to be a significant figure. But zeros get a little tricky, and we'll talk all about that in chapter 2. But zeros get a little tricky. There's some rules you have to follow when you're looking at zeros and whether or not they will be significant. And in some cases, you could have a lot of zeros and they're all non-significant, and in some cases, you have a lot of zeros and they are significant. And we'll talk more about that. Just an example here as well. All of these zeros are actually not significant, and we wouldn't count them. And again, we'll get into this rule. Did you have a question? Question? Yeah, right. It's opposite when you're, so it is opposite when you're, for example, um, if you're starting with a number that's not in scientific notation and you want to put it into scientific notation. If you move the decimal point to the left, like for example, if we had this number here, we would move it to the left, right? One, two, three places, and it would be a positive three in that case. Now, if you have a number again that is not in scientific notation and you move the decimal point to the right to put it into scientific notation, it will be negative. But if you are starting with a number that is in scientific notation and you need to turn it into a non-scientific notation, it's basically the opposite because you're now has to move it in the opposite location. So the easiest way to sort of remember it, honestly, is if you have a positive exponent, the actual number should be a large number above one, and you'll have a negative exponent if that number is really below one. Like number here, this 0.00023, that's less than one, right? So when we put that into scientific notation, it should be negative. When we look at the 3200, that's definitely more than one and a larger number. When we move the decimal point, whatever way we're going to move it, which in this case to the left, it should end up as a positive one. So that sometimes is an easier way to remember it. Kind of a big number, you should have a positive exponent. If it's really less than one or kind of a small number, you should have a negative exponent. Other questions? Yeah, I'm sorry, I missed the first part of the question. Okay. Yeah, so if you're going from a regular number to like scientific notation, is that what you're asking? Yeah, so if you're going from a regular number to scientific notation, the way you should think about it is you need to move the decimal whichever way is going to get you to a number between 1 and 10. So again, if you had 1240 and we know the decimal point should be here. Now, if you're not sure which way you need to move, the thing you have to remember is you got to get between 1 and 10. right? So if I were to move it to the right and add a 0, is that number moving towards 1 and 10? It definitely is not right now. It's getting bigger. So that is definitely not the right way to move it, right? Now, if I take this decimal and move this way, I go from 1243 to 124.3. Is that at least moving towards 1? It is, right? But we're not there yet, right? We got to keep going. So I move it one more time. Now I'm at 12.43. Getting lower, right? But still not a number between 1 and 10. So I can't stop. I got to go one more place. And now I'm going to end up with a number that is 1.243, which obviously is a number between 1 and 10. So that's a way you can figure if you're really not sure sort of which way you need to move it. Um, just move it one way, add a 0, or just move it one way and move the decimal point, and just think, am I getting closer to a number between 1 and 10, or am I getting farther away? And that'll tell you which way you need to move it. Yeah. Yeah. It would be, yeah, it actually is. This original number, all those are significant. And so when I write this, I would need to keep actually all those numbers to 1.243. I remember we started over here, right? So 1, 2, 3, and finish it out times 10 to the 3. And writing it like that will maintain those 4 significant figures. Yeah. 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 So if your question is, we did a calculation, again, we'll talk definitely a lot more about it in chapter 2 for sure. But if 1.243 times 10 to the 3, and we needed only 3 significant figures. In this case, we would get rid of that last 3 and do 1.24 times 10 to the 3. It wouldn't be because when you would turn it back, you would add the 0 back in. And you would end up with 1240 in that case, if you happen to start with that. But at some point, you do have to round off some numbers to try to get to the right answer. And sometimes it definitely will not give you the exact number you have on your calculator. And the point of that is, as we'll talk about in chapter 2, the point of that is your calculation is only as good as your worst measurement. And your worst measurement will kind of have the lowest number of significant figures or the lowest number of decimal places. And that's why we have to eventually round it. Other questions? I promise you we will get back to significant figures for sure in the official chapter, chapter 2. Any questions on the scientific notation part? Yeah. It has to, yeah. So 1's okay, 10's not. So it's got to be less than 10, but 1 point something is okay, or even 1 something is okay. But 10 times something is not. So it's got to be less than. Yeah. All right. Let's talk maybe about something that's probably even more important than writing numbers in scientific notation or any of that, and that is your friendly neighborhood calculator. Yes, and how to properly punch a number into scientific notation on your calculator. So let's talk about how to do this. And again, like I said before, in addition to this, how to do it on your calculator, it's in chapter 1. They do have some other things, I think, how to punch some things into your calculator. So again, there is some helpful information there in chapter 1. But let's talk about officially how you should punch your number in scientific notation into your calculator. I would say most people, frankly, do it wrong, and you will end up with probably the wrong answer in some cases. So let's just start with some important buttons that most calculators have, and that is what I call your exponent button. So if you look on your calculator, you may have a button that's EE. You may have an EXP button. Some of those newer ones, I guess they're not new, they've been making them a long time nowadays, will have a times 10 to the n. These are usually calculators that have like a two-tone paint job, kind of like a main paint color and like a sides a little different. These are your exponent buttons, okay? And I would say on most people's calculator, you could either find that, I would say, right about here above the numbers, or towards the bottom is usually where most people calculate. You can kind of find those buttons. Now, another really important number or button on your calculator is, I call it the negative button. It's really the change of sign button. And on most people's calculators, there's two versions usually. There's one that kind of looks like a subtract, but it has parentheses. Or a lot of ones nowadays have a button that kind of looks like that, like a plus and a minus is typically that. So these are buttons that you use for scientific notation, and it's your exponent button. That we use to change the sign or the negative button, like when you have a negative exponent and you need to punch that into your calculator. Do not use the subtract button because you'll get probably a big old error on your calculator and stuff like that. All right, so let's talk about how we would punch a number in just to make sure. This is probably the most important thing to learn out of this chapter, maybe. Let's see. All right, let's say we had our number 1.25 times 10 to the minus 6. And we wanted to punch that into our calculator correctly. We will start with these two buttons over here. We'll talk about what you need to do if you have a calculator that has that button in a second. But if you have either an EE button or an EXP button on your calculator, this is what you should punch in. You should do 1.25. Then you should hit your exponent button, whichever one of these that you have. Now, probably on your display, you may see a 1.25 and an E pop up. You may see a 1.25 and maybe a couple of zeros pop up. Why not? We'll go for all three options maybe. Maybe you'll see a 1.25 with a really small times 10 and a couple of zeros pop up. But one of those options is probably what your calculator will kind of look like at this point. When you hit this button, by the way, when you hit this button right here, this exponent button, that represents this part of the number. That represents the times 10 part. That means first mistake that people make is they see the times 10 and feel like they need to hit the multiplication button. You should only do that if you want to get the wrong answer. Yeah, so don't do that. Yeah. So when you hit the exponent button, it represents the times 10 part. You should never hit the multiplication button when you're doing scientific notation in your calculator. You should also never do what most people like to do, the inverse log button, where most people look at the calculator and go log 10 to the x. That's it. That's not it, by the way. You will get the wrong answer. So don't use that one. All right, so that means that the only thing left for us to put in is the negative. That is now over here. These are our negative buttons. You hit whichever one you have on your calculator. You hit the negative and then 6. That will put a negative 6 here. That will turn this into a negative 6. That will turn this into a negative 6. That is the proper way to punch a number in scientific notation into your calculator. Obviously, at this point, if you're going to multiply, you hit the multiplication button. Then if you had another number in scientific notation, you put it in the exact same way, okay? First off, any questions on that? Now, if you have that times 10 to the end, and like I said, typically speaking, those are like the two-tone calculators, and they also typically have in the upper right corner of the calculator, upper right of the calculator, they also have like a little wheel action happening. So if you got one of those that's got like a circle wheel happening, it's a two-tone, and it's got one of those. You have to be really careful when you punch a number in scientific notation into your calculator. You have to use parentheses. So let's talk about how you would punch the same number in if you had that calculator. So if you had that calculator, you would erase the wrong button here. There we go. And you would go, first off, the most important thing, you actually need to open a parentheses. So on your calculator, you should have a parentheses button. You would need to open the parentheses. And then you need to hit 1.25 and then your times 10 to the n button. Again, this is not the log button. This is a dedicated times 10 to the n button. On your display, it will look like this. Parentheses, 1.25 times 10. You will now have a little blinking cursor, blinking up on top, if you have this type of calculator. Now you need to put the rest of it in, which is your negative and 6. And now what it will look like, 1.25 times 10 to the minus 6, your little square will be right next to the 6, blinking. And you may think, cool, I just got to close my parentheses. And you would be wrong, because on most of those calculators, you'll get an error, because you're going to make a small little parentheses up on top to go with that big parentheses, so your calculator is going to go no good because I was programmed really crappily, and you're going to get an error. So this is where the wheel comes into play. You go to your wheel that looks like this in the upper right, and you hit the right-hand side of the wheel. And what that will do is bring your little cursor down to a regular size cursor, and now your screen will look something like this with your cursor down here. Now you can close the parentheses, and you end up with something that looks like this. So if you have that two-tone calculator with that button and the little wheel, really all you have to do is put parentheses around every single number that's in scientific notation. If you don't, the way those calculators are programmed, I'll just say it, it's probably programmed wrong. The way those calculators are programmed, it will do the math wrong. So it'll separate the numbers not correctly. So you do have to put those parentheses around it. It looks like a lot, but once you get the hang of it, it's just something that you'll be able to do. You could be a lot sloppier, I guess is a way to say it. Yeah, a lot less careful if you have a calculator that has an EE button or EXP. You don't need parentheses. You don't need any of that. You can roll as many numbers as you want. It'll all be good. But definitely on those kind of newer generation ones and the two tones that have that, you got to do the parentheses around all that. First off, any questions on that? Yeah. You need to hit a shift. Yeah. So if your EE button is hidden, not really hidden, but sometimes that does happen. You got some type of button, but it's got an EE on top of it. You need to go to the shift or the second button, upper left corner of your calculator, and you need to hit that. Yeah. And then you should be in good shape. Yeah, I would assume, and again, we can look at it afterwards, but you would hit 1.25. You would then need to hit actually your shift or second, whatever button you have. Then you would hit that, whatever button that has the E above it. And then, whatever, was it negative something? Negative 6, right? Then you would hit your negative and then 6, yeah. And then you should hopefully be okay. Again, you want to make sure that you know how to do this. This is a really big thing. There's numbers definitely going to be a scientific notation. You want to be able to punch them in correctly. Why don't we try a couple here just to make sure we know how to punch it in. So let's do, let's get rid of this here. Why don't you take 1.25 times 10 to the minus 5. We'll divide it by 3.2 times 10 to the 14. See what you end up with. And why don't we do 4.5 times 10 to the minus 2 times 1.60 times 10. Let's go with 34. All right, so for each of those, punch them in correctly, see what you come up with. I will as well, since I just made it up, obviously. And we'll see how we did. It may not be able to because you may not have enough space, or maybe set to scientific notation. So probably the one that says mode on the right there, you probably have to play with it. Yeah. All right, so let's take a look and see. We'll start with the first one here. So if I was going to punch this into my calculator, and again, I had the EE button or the EXP button, this is what I would punch in, I think. Flip that around so I could write, maybe. All right, so I would go with 1.25. I would hit my exponent button, which stands for this part of it. I would do my negative as it's a negative exponent, and 5. I would hit my divide button. I would go 3.2, once again hitting my exponent button, which is this part. This is actually a positive exponent, so I don't need the negative button here. I would just need 14 and maybe a little equal. If I had the two-tone sort of calculator, I would open a parentheses, 1.25, hit my exponent button, hit my negative button, hit my 5, hit my will, and close my parentheses, then hit my divide button, open a new parentheses, go 3.2, hit my exponent button, and that's positive, so I'll go 14. Once again, hit my will, and close my parentheses, and hit equals. On any of those, you should end up with, I don't even know, let me punch into my calculator, I lost it, let's see. All right, all right, so 1.25 to the negative 5 divided by 3.2 to the 14. I'm going to end up with, on my calculator, I'll come down here and show it. I got on mine something like 3.90625 E negative 20 is kind of what my display sort of shows. Now, again, your display may show it like this. 3.90625 times 10 to the minus 20. You may even have a calculator that will show it 3.90625, kind of like a big space with nothing written, and then like a minus 20. Yeah, so you may even see it in that kind of aspect. First off, is that everybody gets something like that. Now, if you got the front part of the number, but the minus 20 not so good, you didn't punch it in correctly. Most likely, you did not use your exponent button right. And that is a good way to know if you're punching this in correctly or not. If that front part of the number, the one before the times 10 is good, but the exponent is off like by 1, you punched it in wrong. Yeah, is most likely the case in that case. All right, so the answer we should end up with is 3.9 times 10 to the minus 20. We won't worry about the sig figs, but that is where it should be rounded to, which, by the way, this would have how many significant figures? 2, right? Now, really also important when you get an answer like this is people always forget this part of the number. Yeah? They just write the front part and just go, cool, my answer is 3.9. And your answer is going to get a big X on it, which you don't want, right? So don't forget the times 10 part of the number, especially if it gives it to you in scientific notation. Also a reminder that your calculator may not always give you the answer in scientific notation. It may just give it to you in decimal form. So that's okay too, yeah? You may just have like some other type of number there. Question? Yeah. We do, and again, we'll talk more about that in chapter 2, but that's what it should be based on that calculation. Question? Yeah, if you had that many spaces on your calculator, in decimal form, you mean? Yeah, then it should be okay. You will just have, you basically have 19, you have 20 zeros? Yeah. You have 19 zeros before the 3, right? Yeah, 19 zeros before 3. Which, is that on the Excel or something, or is that on your calculator? Yeah, that's very unusual that a calculator would have that much room, to be honest with you. A lot of times calculators will run out of room and they'll force the answer into scientific notation just by themselves because they do run out of space. So when you do a calculation, it may actually put your number in scientific notation because it runs out of room to do it in decimal form. Or if you have enough room, a lot of times, most people's calculators are programmed just as like decimal answers. They'll just put the answer down non-scientific notation. So that is 2 options as to what might happen there. Let's take a look at the second one there. Let's go with how we would punch it in. We'll go 4.5. Once again, our exponent button. We'll go our negative button and 2. We will hit our multiplication button. 1.6 exponent positive 34 and equals. Obviously, if you have the one with the wheel, you got to do the parentheses like we were talking about as well. And if you punch that in there, that's going to be 4.5 to the negative 2 times 1.6 to the 34. And that's going to get me on my display. Looks like I got a 7.2 and on my display E32, I think. And again, you may have 7.2 times 10 to the 32. You may have 7.2, a little space and a 32 to the right. Again, you do not want to forget the exponent part. Now, our answer here will be 7.2 times 10 to the 32. And when you are writing a number in scientific notation, you should always write it with the times 10, not the E. So that's also a common error that people make. Because we do use this E as like a exponent sort of substitution, when they give the answer, they would write something like this. Don't do that. Write it as times 10 when you're writing it. Any questions on that there? All right. If you're still having trouble with your exponent button, at some point, just come see me. We'll figure it out on your calculator if you're not sure. Okay, we're going to continue on. Any questions on what we were talking about in terms of scientific notation? So again, a reminder, as I mentioned, you are responsible for chapter 1. Again, there's a lot of math review, calculator type stuff, so definitely make sure you look at it. I would say probably the main topic out of chapter 1 that you for sure will see and are super responsible for is scientific notation, being able to write a number in scientific notation, being able to take a number from scientific notation into decimal form, and probably, again, as we talked about there at the end, the most important thing, being able to properly punch it into your calculator. And that's, the main sort of part of chapter 1 that you're really responsible for. But again, I would review it if you need some help in any of those areas. I don't know there'll be any specific questions on adding negative numbers and that type of stuff. You may have to do that type of math. So again, it's just more so for review. So the main real topic, which again is usually in chapter 2, is the scientific notation part of it, okay? So with that being said, we are going to go to chapter number 2, which is really the main start here. And we are going to definitely cover everything in chapter 2 for sure. And chapter 2, we're going to get into measurements. We are going to get into how to take a proper measurement. We're going to get into everybody's excitement from chapter 1, definitely about significant figures, how to calculate significant figures, how to do calculations with significant figures. We will talk about conversions and doing problems, which is known as dimensional analysis. And we will finish up the chapter talking about density. Okay, so there's a lot kind of, like most of these chapters, there's a lot kind of bundled into this chapter. All right, so let's get into it. So let's talk a little bit about measurements. And one of the most important things when you take a measurement, when you record something, is you always want to record a measurement sort of correctly. And one of the very, very common errors that people make is they go do some type of measurement, and this is what they record, 125. What am I talking about? I have no idea. Could be $125, which would be great. Could be 125 pennies, still great, could still buy something maybe in the drive-thru with them. Could be 125 apples, still good if you like apples, make some apple pies. But a number by itself is not a measurement. A number by itself does not tell anybody what it represents, what it is in relation to. So you should always have accompanying in a measurement a number and a unit. And I can't tell you how many people do not put the unit in. And without a proper unit, the number is really irrelevant because nobody really knows what it is representing. So always get into a habit, especially when you're in the laboratory, to record measurements properly. And that should always be, as we will talk about, to the proper number of significant figures and also to with the proper units associated with it. Now, when we talk about units, there's really two types of units that we come across. There is what is sometimes referred to as the English units or the US units. And then there's pretty much the rest of the world, which rolls with the metric. Yeah. And those are really the two sort of types of units that you come across. As you can see here, we have an example of each. 22 degrees Celsius metric, we roll with temperature in Fahrenheit, right? 72 degrees Fahrenheit outside. Nice day. You go to the doctor, whatever, they may weigh you in kilograms, which is metric, but we usually roll in pounds, right? So that's a different unit. Right, you look on your car speedometer, still may do it. Maybe not so much with digital ones anymore, but you maybe have an older type of speedometer. They have miles per hour and kilometers per hour, right? Because again, that's metric, right? I think on the digital ones, you got to punch a button to get it to do that these days. But they have both of those things. So there's definitely two different types of units. And like I said, pretty much everybody kind of rolls with the metric. We roll with the English or US units. And as you can imagine, it can cause a lot of trouble, especially when the world gets smaller, people are doing business. You're doing something with somebody maybe in Europe and they're rolling with metric and you're doing all your measurements in English or US and inches, and things don't work so well. It's really why sometimes there's some disasters that occur because people use a metric fitting when they measured in an English sort of unit, and it's not the same. So around 1960, they had actually a conference on weights and measures. Sounds like fun. And what came out of that is they decided like maybe we should just have like a standardized system of units that people use like in science. And that is, as it mentions there, what is referred to as the SI unit, which stands for the International System of Units. And for all intents purposes, it's pretty much metric-ish. So kind of metric one out there. But you'll oftentimes see like the SI unit for volume is this, or the SI unit for mass is that. And this is sort of this standardized sort of system of units that is used a lot of times in science for things like length, volume, mass, temperature, and time. And if we take a look at a table from your book, for example, volume, the metric unit is liters. The SI unit is meters cubed. For length, the metric is meters, and the SI unit there is meters as well. Mass is grams in the metric, but the SI unit is kilograms. Temperature, this might be one that maybe you're not familiar with. For metric, it's degrees Celsius, but for the SI, it's a unit of Kelvin. Pretty much a safe bet, as we'll talk about as we go through the different chapters. If you ever come across a temperature value and you kind of need to use it in a calculation, there's a pretty good chance that your temperature needs to be in Kelvin. And that's kind of like almost like a standardized temperature unit that's used in chemistry for sure. It's very hard to even think of a formula where we kind of keep the temperature in Celsius. Only one comes to mind. All the rest are pretty much Kelvin it needs to be converted to. Time is second in each of these things. Also, it's really important when we think about units to understand what they represent. So if you have some type of mass, those units are perhaps kilograms, grams, and stuff like that. That is not a volume, right? I can't tell you how many people sometimes have told me, I asked how much did that weigh? And they're like, yeah, the volume was, 52 liters, And I'm like, or 52 grams was the volume. And I'm like, that's not a volume, right? So grams. So you want to make sure that you understand what those units represent. Does it represent a length? Does it represent a mass? Does it represent a temperature or a volume? Now, you may be wondering, cubic meter sounds more like a length. And when you take a length measurement and you take three length measurements, like length times width times height, and let's just say they were all measured in meters times meters times meters, each of these individual measurements, these are all length measurements. But when you multiply them together and you get a cubic meter, that is actually a volume. So that is one way you can get a volume of an object, is actually, especially if it's like a cube or something like that, you could actually measure those three sort of directions. And when you multiply three length measurements together, you actually end up with a volume. So you end up with a cubic volume there. So let's talk a little bit about a volume. As I just showed there, the SI unit for volume is cubic meters. I would say probably in terms of volume, cubic centimeters is more often what you come across. And again, that also is achieved by doing the same three length measurements, length times width times height. If you measure them all in centimeters, you will end up with a cubic centimeter that once again is a volume. And again, each of these are length measurements. Now, I would say a milliliter, 1 milliliter is the same as a cubic centimeter. They are a one-to-one relationship between those two. You may also be familiar with a cubic centimeter as a cc, right? Give this guy 5 cc's of this before they die on those medical shows, right? Or whatever it may be. Or maybe in real life as well. Um, and that's also a cubic centimeter as well. So they're all a one-to-one relationship between them. I would say in terms of, again, volume units, cubic centimeters is common, milliliters is common units, and liters are also probably your big three in terms of units for volume is those three. The relationship between a liter and a milliliter is 1 liter is 1,000 milliliters. And that is something that you probably should know because it's just used a lot. So a lot of times we do take measurements in milliliters, but a lot of times in calculations, we need the volume to be in liters. So that conversion between milliliters and liters, and also going from liters to milliliters, is a conversion that's used a lot. And again, there's 1,000 milliliters in 1 liter. By the way, when we do a volume, graduated cylinders are really good pieces of equipment to read. And when you have a liquid in a glass container like a graduated cylinder, professionally non-drawn there, the liquid will curve, and that is what is known as the meniscus. And the meniscus is the curvature of a liquid, and whenever you take a volume reading, you always usually want to read from the bottom of the meniscus, especially if your meniscus is a U-shaped meniscus, which I would say in most cases that is what you're going to come across. And the reason for that sort of U shape of the liquid is, as we'll touch upon in a later chapter, the attractive force between the liquid and the glass is actually stronger than the attractive force between the liquid and itself. So what happens is the liquid on the sides that are touching the glass starts to rise through capillary action and start to go up the glass and kind of rise up the glass because of that attractive force. That is why we read from the bottom of the meniscus, because in the bottom of the meniscus, it's not touching the glass, and that's the true volume. If they didn't have that attractive force that made the sides go up, it would come back down to exactly where it is in the middle of the meniscus on the bottom, and that's why we read from the bottom of the meniscus. I would say that most solutions or liquids will do that. It can have a meniscus that actually goes in the opposite direction, probably the only one that does that. And again, you won't come across it because they've taken mercury out of the labs. many, many years ago. But mercury actually goes the opposite way. And you would actually read from the top of the meniscus in that case. So most of the time, your meniscus is going to look like that, like a U shape. And sometimes it's easier to see than others. If you have a smaller diameter glassware, a little bit easier to see it. If you try to use a really big beaker to measure out liquid, you're going to find yourself way off because you won't be able to correctly see that meniscus. And when you fill it up to the 200 line, you probably only have 150 in there because you're way below it. And people will sometimes use the wrong pieces of glassware to take measurements, and a beaker is a terrible piece of glassware to measure out a specific volume. A graduated cylinder like that is a much, much better piece of equipment to do that with. Any questions on that? So as I mentioned before, here are some, I feel like the T's missing there. That is some conversions for volume. Once again, that top ones we come across. I would say the quart in the milliliters to quart one does pop up a good amount in this class in some questions, maybe online and homework type questions. So this was probably a good one to think about as well. It does sort of pop up every so often. Let's talk a little bit about length. Length units are SI units is meters. I would say very commonly centimeters is used in terms of length. So meters, centimeters, millimeters are very common sort of units that are used, along with some other ones along the way. If you look at a ruler, right? Standardized ruler, up on top is inches, right? On the bottom is centimeters, yeah? The small markings between the centimeters are millimeters, yeah? So if you look at a kind of a standardized ruler, or normal ruler, inches are up on top, the big markings. Big markings on the bottom are typically centimeters. The little markings are usually millimeters when you look at a regular sort of standardized ruler. And obviously different ones will have different sort of markings as well. There is a relationship that does pop up a lot, and that is 1 inch, which is a English unit, is equal to 2.54 centimeters, which obviously is a metric. This is what is known as an exact conversion. So in 1 inch, there's 2.54 centimeters, and that is oftentimes referred to as an exact conversion. In 1 meter, there's 100 centimeters, which is a good conversion. That one as well. Again, does pop up a lot along the way. By the way, when we do look at these things like this, when we look at something that is 1 meter is 100 centimeters, this is what is known as an equality. Yeah? And an equality is two different values that are on two different unit scales, but they represent the same amount of something. So if you say that is 1 meter in length, that's the same as saying it's 100 centimeters in length, right? Just like if you had 100 pennies, that is the same amount of money if you had $1, right? So they both represent the same amount of money, but they're on different units, and that's what an equality is. As we'll talk about later on in this chapter, you could use an equality to get conversion factors to do some conversions. Obviously, these are all equalities here. Mass is the of an object is the amount of material that it contains. When we talk about mass, there is a difference between mass and weight, and sometimes people will kind of use those words interchangeably. So the mass of an object and the weight of an object are different. Weight takes into account the force of gravity. This one is independent of gravity. So one of the ways that we measure mass is on a balance, and a balance is what we see there. That's an electronic balance. Balance is a fancy word for a scale. Yeah, so that's basically what that is. And When we measure something in the laboratory, we do the process known as weighing, but we do not record it as a weight. So it is recorded as a mass. And that's because the balances do take out basically the force of gravity. That's the way they're made. So the mass of the object is what you should refer to it. The mass of an object here and the mass of an object, say, on the moon are going to be the same. But the weight of the object here and the weight of the object on the moon will be different because the force of gravity is different between here and the moon. It's like 1/6 of it. So the weight of that thing will be different, but the mass will be the same. So when we do weigh out something in the laboratory, we do refer to it as a mass. And just a heads up, whenever you take a reading in the laboratory of something that is digital display, all the numbers are important. You should always record all the numbers. So my favorite is, everybody comes out with, I sat there all day and got exactly a 5, 5 dead on the nose. I was there all day, scooping everything in. Makes people wonder sometimes when people say that. So you should always record anything that's digital to the prop. All the digits that are there, they're all displayed because they are important and they're actually all significant in that case. Common units, kilograms and grams are very common units of mass. And in 1,000 grams is a kilogram. 1 pound is 454 grams. You'll sometimes see 453.6 grams as 1 pound. I would say these two definitely pop up a lot in chemistry, those sort of equalities and conversions. Temperature. There's actually 3 types of temperature scales that we come across in chemistry. There is degrees Celsius, there's degrees Fahrenheit, and there is Kelvin. Now, one of the major differences between those is how I said it and how you write it. There is degrees Celsius, there is degrees Fahrenheit. It is just Kelvin. We do not use the degree sign. We do not say degrees Kelvin. It is just the number in Kelvin is how we refer to it. So if you had 298, that would be 298 Kelvin as opposed to 298 degrees Fahrenheit, kind of hot, and 298 degrees Celsius, right? So we don't use the degree symbol, that little circle on top, and we don't say degrees with Kelvin. Kelvin was named after a guy named Kelvin. It seems logical. But it actually used to be called the absolute temperature scale, obviously later renamed for Kelvin. But Kelvin is really, honestly, it is really the temperature unit that we use here in chemistry. I would say outside of the opening chapters, you probably won't see degrees Fahrenheit pop up too much at all in chemistry. Celsius, definitely. And that's because, for example, in the laboratory, we take measurements usually in Celsius on the thermometer and then has to convert it to Kelvin. There is differences in where water freezes and boils on these different scales. Water freezes at 0 degrees Celsius and 32 degrees Fahrenheit, and it boils at 100 degrees Celsius and 212 degrees Fahrenheit. In terms of water, where it boils and where it freezes are 2 values that are probably pretty important to know. It does pop up in some different chapters as well, kind of the normal freezing point of water and the normal boiling point of water. For Kelvin, 0 Kelvin is as low as you can go. There is really no negative Kelvin. 0 is as far down as you could go. So the differences between kind of where water freezes and where it boils is how we kind of get the ways that we convert. I will put it here. We won't go too much into it. I think it's in chapter 3 officially, but since we're talking about it, if you want the temperature in Kelvin, you take the temperature in Celsius and you add 273. The real number is 0.15. Most people leave the 0.15 off and just use 273. If you have the temperature in Kelvin and want Celsius, you take the temperature in Kelvin and you subtract the 273.15. And once again, you're perfectly good to just use, if you want, 273. Most people use just 273, not the 0.15 part of it. Only one school I teach at makes everybody do the 0.15 for some reason. So that's how you do that. In terms of converting between Celsius and Fahrenheit, you may be familiar with it. Temperature in Fahrenheit is equal to 1.8 times the temperature in Celsius plus a 32. And the temperature in Celsius is the temperature in Fahrenheit minus 32 divided by 1.8. That 1.8, by the way, is maybe a fraction you learned when you were younger, 9 over 5. Yeah, is 1.8. Same deal. You could use that as well if you like. Again, outside the kind of the opening chapters, probably not going to see too much Fahrenheit. Definitely, I would say, as we go through chemistry, these are the two conversions that you'll use the most for temperature. And really, most of the time, I would probably say going from Celsius to Kelvin is probably what you're going to do there, which is basically just add 273 to it. Um, if you did have a value in Fahrenheit and you wanted it in Kelvin, you do have to take Fahrenheit to Celsius and then Celsius to Kelvin, and vice versa. If you have it in Kelvin and want to go all the way down to Fahrenheit, you got to go from Kelvin to Celsius, Celsius to Fahrenheit in that. Again, I think in chapter 3 is the official place where we do the calculations, and we'll talk more about that. But really, in terms of just temperature calculations, for sure, that's the one you kind of want to start thinking about, and we'll use the most as we go through it. Yeah. Yeah, you will have to know the temperature conversions at some point for the exam, yeah. And like I said, I think officially we cover it in chapter 3, kind of the calculation part of it. But yeah, you'll need to know how to do that. And like I said, after sort of the first couple of chapters, just knowing really this Kelvin to Celsius or Celsius to Kelvin is really the one you should definitely focus on, because those are the ones we're going to use pretty much most of the time. And you want to be able to just be able to do that because you'll be using it in conjunction with other calculations, right? And part of a calculation. So you don't want to try to think about like how to convert it to the right units. You just want to be able to do that so you can then put it into the formula and kind of use it. Other questions? All right. In general, like I said last time, you are responsible for most of the formulas, but conversions and constants and those type of things will be given to you. Okay. All right. Time is seconds. We'll talk about it. All right. We should be familiar with seconds, I hope. Yes. By the way, if I had a minute, right? How many seconds are in that? Yeah. And if I had an hour, how many minutes are in that? Well, that got a lot quieter. That was a little scary. That is 60 minutes, right? And if I have a day, how many hours are in that? Yeah, it's only 24, not 60. I don't know how many exams I've seen over the years, 60, 60, and they're like 60 hours in a day. All right, so some of that may not be provided for you, so hopefully you should know some of those things. So I'm like, that's like way too many hours, I think, in a day. All right. Any questions on that there? So for each of these, take a moment here and think about what does each of these units represent? Um, is it a length, a mass, a volume? So take a moment. Okay, let's take a look. So 2.6 kilograms, that should be that sounds good. 1.7 meters is length. 0.5 grams is mass, and 1.5 liters is volume. I like it. All right. I think we agree with that. That's good. All right. So as we talked about the sort of SI units for each of these. Again, a reminder, volume is cubic meters. As I mentioned before, probably cubic centimeters, milliliters, and liters are going to really be the volume units you're going to see the most. But the SI unit there is that. Kilograms, definitely used a lot for mass, as we talked about, is the SI unit. Other ones, as we mentioned, grams, milligrams are used a lot as well. Meter for length, centimeters, millimeters, definitely used. And obviously Kelvin is the big temperature unit there for our SI. All right, so take a moment here for each of these. We want to look for which one is the SI unit. So take a moment and see what you come up with. All right, so let's take a look. We're looking for a height. Which one should be the SI unit? It should be meters, right? Is the SI unit. They're all obviously length measurements, but again, the SI unit there is going to be the meters. How about the mass? Which one should it be? Yeah, it should be two there for kilograms. Again, the other ones obviously are mass units, but not again the SI unit. And then temperature should be one. Tic tac toe. Perfect. We got one all the way across there. Any questions on those there? All right. What's that? Yeah, so here we were looking specifically for the SI unit. Yeah, so that's the one, which is basically like the metric unit is pretty much what it would be. Questions? Yeah, no? Go. All right, then let's get into measured numbers and significant figures. Now, there's really two types of numbers that we come across. There are measured numbers, which are numbers that, much like the title implies, you did some type of measurement to get them. And with measured numbers, they will have a specific number of significant figures based on how you did the measurement, what equipment you used to do the measurement. There's another type of numbers which are known as exact numbers. Now, exact numbers are really one of two things. They are either definitions, like we just saw earlier, 1 inch is 2.54 centimeters exactly. So that is considered an exact number. The other way that we get exact numbers is something that we would just count. For example, if we had two baseballs sitting on a field, we're not going to go figure out some type of really big experiment to figure out how many baseballs are there, right? We're just going to count how many baseballs are there. Classic textbook example, basket of apples. You're just going to count how many apples you have in the basket. So those are considered exact numbers. So you may be wondering, what is the difference between, for example, an exact number and a measured number? The difference is actually the significant figures. So when you have a measured number, as I just mentioned a second ago, it will have a specific number of significant figures based on how you did the measurement. Exact numbers can actually have as many significant figures as you want, kind of whatever we want to call it. You could go, hey, I want to give it 6 significant figures, 7, 2, 3, 4. So the main difference between measured, which has a specific number of significant figures, and exact numbers, which can have an unlimited number of significant figures, is where this really comes into play is when you do a calculation. And when you do a calculation, as I mentioned earlier, you always want to have the goal of giving your answer to the correct number of significant figures. Now, when you have an exact number in that calculation, like maybe I use that as a conversion, the 1 inch is 2.54 centimeters. I don't have to worry about the significant figures with that number, just because it's exact. I could kind of ignore it. And I would only have to look at any number in my calculation that really was derived as a measurement. And that's what's going to determine how many significant figures my answer should have. So let's take a look at measurements and how to take a proper measurement. So we'll start with the classic ruler. That's not too bad. I'm going to close my ruler on top. Semi-straight line. They didn't have quality control at the plant there. All right. So we're going to go centimeters here. Now, whenever you use any piece of equipment, be it a ruler, be it a piece of glassware, I'll go right about there. There's usually two types of numbers that you see on the scale. One is sometimes referred to as the large markings. And the large markings usually have numbers next to them, like a 1 and a 2. Yeah. So when I look at this particular ruler here, the difference between my two large markings is how much? What's the difference between 2 and 1? That is not the trick question. If I said 2 minus 1, it equals what? Yeah, right. It's only a 1 centimeter difference, right, between the 1 and the 2. I know it's late. It's all right. You're like, it's got to be a trick question. I can't really just be 1, can it? Now we also have small markings on the scale. So when you look at a scale, you'll see these larger markings that actually have numbers. You will actually see small markings. And typically the small markings do not have numbers. And you want to really count up how many small markings there are between those large markings. Now, it's really important to count it correctly. So when we start to count the small markings, we always start after the last large marking. So if we look at our ruler, my 1 here is the last large marking, right? So when I count the small markings, I'm going to start counting here. That is 1, that is 2, that is 3, that is 4, that is 5, that is 6, that is 7, that is 8, that is 9, and we stop counting at the next large marking. So you always want to start counting after the last large marking and go all the way to the next large marking and stop counting. I lost track there, but I feel like it was 10. Does that sound about right to you? So there are 10 markings in between the large marking. Double jeopardy question is, what does each of the small markings represent in this case? Each of the small markings represents 0.1 centimeters. You could get that by simply taking my large marking and dividing it by how many small markings I have, right? That means that this first small marking, 1.1, yes, 1.2, 1.3, 1.4, 1.5, 1.6, 1.7, 1.8, 1.9, and 2. I drew enough lines. That's good. First off, any questions on it there? Got it. So now that we understand, and by the way, you should do this on every piece of glassware that you use because the scales will be different. Even if your neighbor is using the same piece of glassware, the scale on yours may be different than theirs because they bought it from 2 different people. Yes, so they might have made different scales on it. So you always want to get in a habit, especially if you're taking measurements, to make sure that you do look at the scale and try to figure those 2 things out. With those 2 things figured out, you can now take a proper measurement. So let's talk about taking a proper measurement of my arrow. There should always be, when you take a measurement, numbers that everybody should agree upon. Those are sometimes referred to as certain numbers. If everybody looks at this scale here, everybody should agree my arrow is at least how much? Yeah, it's at least 1.5, yeah? Definitely not exactly 1.5, not really 1.6 yet, right? So it is at least 1.5, and you should record those numbers. These, again, are what are sometimes referred to as all the certain numbers. Now, as you can see from my arrow, it is not exactly at 1.5, as I just mentioned. It's not really at 1.6. It is somewhere in between, I would say. Step by straight line there. We'll kind of go with that. This is where the estimation comes into play and the uncertainty. So whenever you take a measurement, there is always going to be some degree of uncertainty with that measurement because of the scaling. Because I may look at it and go, I think it's this. Somebody else may look at it and go, I think it's a little bit more or a little less than what you said. That is where the uncertainty comes into play. Now, when I look between 1.5 and 1.6, maybe in my case, I don't feel it actually got halfway there in my badly drawn scale there. So maybe I think it's just before half. I would record 4, and obviously the units. This is what is sometimes referred to as the first uncertain number. And when you take a measurement, you should always record all the certain numbers, which again, there really should be no room for argument on that. No matter who looks at it, everybody should agree. And the first uncertain number, where maybe there could be some disagreement about what that would be. Now, when you take a proper measurement and do that, that is really important because when you do that in a measurement, that is the significant figures. Which means my measurement I just took has how many significant figures? It has 3. The uncertain digit is which one? The 4 is where the uncertainty is. Typically speaking, you're saying, well, in this case, I think it's 1.54, but maybe it's 1.55, maybe it's like 1.53, somewhere in that ballpark, it's in that range. The uncertainty lies in this case in the second decimal place. First off, any questions on that? Now, again, it's really important to look at your scale. So if you had, say, something like a liquid in a graduated cylinder. Oh, that's definitely not buying from this place again. That's 20. That's 30. We'll go milliliters here. We'll pop a liquid in there, which should have a meniscus, right? A little curvature. All right, so on this particular scale, my large markings represents how much? What is the difference between the large markings? It is 10. 30 minus 20 is 10, right? So each of the large markings represents 10 milliliters as well. Now, when we look at this, we again want to count the small markings. So we're going to start with after that last large marking. So that's going to be 1. That's going to be 2. That's going to be 3. That's going to be 4. That's going to be 5, 6, 7, 8, 9, and winning 10. So that means each small marking in this case represents how much? It does represent 1 milliliter. Again, I could take my large markings and divide it by 10 because there's 10 small markings. 10 divided by 10 is 1 milliliter. In this scale, this first line is actually 21, right? 22, 23, 24, 25, 26, 27, 28, 29. Definitely no quality control there. Now, we want to take a volume reading now. And again, this is really what you want to do every time you take a measurement. You want to figure those two things out because that's going to allow you to take your reading to the proper number of digits. So for sure, if we look at my meniscus, we'll just kind of freehand it that way. It is at least how much? Yeah, it's at least 24. That's going to be, again, our certain numbers here, right? So we're going to go with 24. Once again, it's not exactly at 24, not quite there at 25. Here we want to kind of think about maybe, is it halfway there, more than half? Is it closer to the end? By the way, you don't always have to go with a 5, right? If it looks closer to the next marking, you could go with an 8 or 9 or something like that. If it looks closer to the previous marking, you could do like a 1 and 2. Some people think, oh, it's not exactly on, I just put a 5. But you do want to actually look at it and see where it's sitting and how it's close to it. So again, in this case, I would say it's probably a little bit, that's definitely not the straightest line known to man there. I think kind of like in that area. I would say it's a little bit above the half. So maybe on this one, we go 0.7. That is all the certain numbers, right? Plus my first uncertain number. And I also want to always record my units, right? By the way, that would mean this one has how many significant figures? It does have 3 sig figs, right? In this case. Uncertain value or estimated digit is 7. Yeah, so that's where the uncertainty. Typically speaking, plus or minus 1 of that uncertain number is sort of what we sort of associate with it and what you want to kind of do. Now, it's really important to look at the scale because, for example, if you had, and we'll put it right about there. All right, so we take a look at this one. Yeah. Yeah, that's why it's the uncertain part of it. Yeah. There, so typically speaking, when you look at a measurement and you find the uncertain sort of value there, it's usually considered like, okay, it's somewhere within plus or minus one of that uncertain digit. Like I did earlier, I think I said like it's maybe 25.4, but maybe it's like 25.3 or 25.5 is sort of where that is. Some people will say plus or minus five of that last one, but it's somewhere in that ballpark. You kind of want to be where the uncertain digit is, you know. So that's why, like I was saying earlier, if it looks like it's like near the marking, right? You wouldn't put five, right? Or you wouldn't put one, right? You might put like eight or nine as that last digit, right? Or if it looks like it's at near the first marking before you get to the next one, you might do something like a one, a two, or something like that. So you want to kind of visualize that difference between those two markings, and you can kind of break it up evenly and try to figure out, you know, about where it is in that marking. All right. Largest marking on this one is it is 10 milliliters. Again, we have a 20 and a 30. So if we subtract those two, we got 10 milliliters. We're going to count our small markings in this case. Again, we're going to count up starting here 1, 2, 3, 4, and 5 in this case. That means my small markings are how much? It is 2 milliliters. Once again, you can divide that by 5, which is the small markings, and you get 2 milliliters. That means in this case, that's a 22, a 24, a 26, and a 28. So even though the large markings on this piece of equipment is the same as the last one, the small markings are not. So the scale is different here, right? And that's going to measurement take place. What happens when you buy like a cheap one versus maybe a more expensive one? Or you got a little bit more markings on the expensive piece of equipment. Now, when I look at this, I'm sitting right about here, right? That is between 22 and 24. What number comes between 22 and 24? 23. On this particular one, that is it. That is the best you can do because there is no way you would know between these two numbers exactly where 22 stops and 23 starts, right? There's just no way to know, right? Not enough distance. We could make that estimate when it's only like a one difference, right? You go halfway, it's halfway there, right? So it's a 5. But here we don't know where 22 stops, don't know where 23 starts. The best we could do on this particular measurement is 23 milliliters, which makes me ask you, how many sig figs is that? That is two significant figures. Which one would be the uncertain number? 3 is our uncertain, our estimated digit, right? We're basically saying, I think it's 23, maybe it's 24, or maybe it's 22. It's the best I could do on this piece of equipment. As opposed to here, where I could say it's 24.7. Which one's a better piece of equipment to use for measurements? This one, right? Because you can definitely go to the tenths place, I'm uncertain. Here, on the ones place, I'm uncertain, right? Bigger area of uncertainty. You have this much uncertainty in this one. Here you have like that much uncertainty, right? So it's a much better measurement on this one because you have more markings and you can take the reading to the proper number of digits. Any questions on that there? So it is really important to look at the scale, and it can differ even if the equipment's the same, like volume or whatever it may be. Depending on the number of markings, it can limit how far you can take that reading. And when we talk about calculations, that's important because you're only as good as your best measurement. So if I ended up using this one, that's going to probably be my worst measurement, right? You're only as good as your worst measurement. That's the best I could do when I'm done calculating something, as opposed to here, I could do a lot better, right? I could at least take it out to another decimal place. One last thing before we finish up here, which is, typically speaking, you could go one more place to the right of the smallest marking. So on this first one, right, our smallest marking was first decimal place. Our answer went to one more place to the right, which is the second decimal place. Our smallest marking on this one was 1 milliliter, whole number. One more place to the right is where we take the reading. Not always, because in this case, we couldn't, right? So there is a simple way if you're like, I for sure can figure out what the large markings mean and what the small markings represent. If you are for sure confident in what the small markings represent, all you have to do is take the small markings value and divide it by 2. So if we do it on this one, and I take 0.1 divided by 2, that gives me essentially plus or minus 0.05 centimeters. That's how many decimal places? 2. My answer is 2 decimal places, right? If I come over here, smallest marking is 1 milliliter. If I take my small marking, which is 1 milliliter, divided by 2, gives you 0.5 milliliters. That's how many decimal places? 1. My answer was 1. Even on the weird one, smallest marking is 2 milliliters, right? If I take 2 milliliters divided by 2, I get 1 milliliter, whole number. Measurement went to a whole number. So if you're confident that you know what the small markings represent in terms of value, all you have to do is divide it by 2, and if it goes to 2 decimal places when you do that, take your reading to 2 decimal places. If it goes to 1 decimal place, take it to 1. Whole number, take it to whole number. Any questions on that? Good, because I need a nap. All right.